Okay, so last time we gave some context and motivation for the following definition. So a space X is compact if every open cover of X has a finite subcover. So let's see some examples. This is a definition that definitely takes some time to get used to. So first example, R, the real numbers, is with the standard topology not compact. Since, well, to show a space is not compact, all you have to do is find a single open cover that doesn't have a finite subcover. So since the sets, let's take these open sets, these cover are and don't have any finite subcover. Okay, so the picture is like this. So we can definitely cover R by sets like this, length 2. But no finite subcollection of these is going to cover. So R is not compact for this reason. I want to make one important point here. So note that R is the union of two open sets. So, for example, these two, R has a finite cover, but this is irrelevant to the question of whether or not R is compact. So, in fact, any topological space has a finite cover. Namely, you can just take the space itself, since by assumption for topological space, X is open. Finite open cover. But that's not what compactness is about. Compactness says that every open cover, no matter what it looks like, it has a finite subcover. Let me give you another example. So let's take X to be 0 together with the numbers 1 over n. Topologized as a subset of R. So this is compact. So here's how X looks. So you have 1/2, 1/3, 1/4, and etc. And okay, so let me try to convince you that X is compact. So what we have to do is to show that, so let's let U be any open cover of X. So to show X is compact, we have to start with some open cover, and we need to find a finite subcover. So we don't really know what U looks like. All we know is that U contains every point of X. U is a collection of open sets, and each point of X is in one of these open sets. Okay, but so what we can do is, so there exists some U naught in U, script U, so that 0 is in U naught. Every point in X is in one of these open sets, so let's call the one containing, there's at least one containing 0, let's call it U naught. And well, there's since U naught is open, there exists some R, so that the interval from minus R to R is contained in U naught. Okay, so we find that there's some small interval here around 0, which is contained in U naught. So now, well, the point is that this interval here, this contains all but finitely many points of X. And so for each of the points that are not contained in here, we just choose one of the open sets in the cover that contains that point. And then the result is a finite subcover. So, so U naught contains all but finitely many points of X. Maybe let's call them, X1 up to XM, and we can choose UI in U with XI in UI. And so then U prime being U naught up to UM, this is a finite subcover. Of script U. Okay, so this finishes the proof. So let me remind you that one of the reasons why, or the way we came upon this notion of compactness is from, well, let me just tell you this, state this theorem that I stated last time without going into everything I said. So the Heine-Borel theorem says that X subset of Rn is compact if and only if X is closed and bounded. So we're going to prove this theorem eventually. But before we get there, so the first thing I want to do today is to give you some more motivation for what compactness can do for you, why it's a useful property. And well, yeah, and before that, let me start by let me give some more examples illustrating this theorem. More examples of things that are compact or not compact. So, okay. So one consequence of this theorem is that the closed interval 0, 1 in R is compact since it's closed and bounded. And actually an important step in proving the theorem will be to prove this special case. But using the theorem, we can also give lots more examples of subsets of Rn which are not compact. So for example, so Q squared is in R squared. This is not compact because it's not bounded. Even if we were to intersect it with the unit square, now it's bounded, it's still not compact because it's not closed. Well, we could have said this here as well. It's not closed, not bounded. And another example, well, if we just consider R as a subset of R squared as maybe the x-axis, this is also not compact. So here, this example is closed, but it's not bounded. Okay. Right. Okay, so I want to tell you a couple of results, or maybe it's just one. No, there's two, about compact sets that relate to continuous functions. So the first is about the image of a compact set under a continuous function. And briefly, it says the image of compact is compact. So let's take f from x to y, continuous. So then, and let's assume x is compact. So then the image of x, so this is y and y, which are equal to f of x for some x. This is compact. Okay, so this is a useful proposition. The image of a compact set is compact. Let's prove it. And these are, this is maybe also a good warm-up for working with this definition, proving things using this definition of compactness. So we want to show f of x is compact, the image. So let's take an open cover of f of x. So we have a collection of open sets which cover the image of x, the image of f. So then, well, consider the collection V, which is f inverse of u, where u is an element of script u. So this is an open cover of x. So it's, these sets are open because f is continuous, and they cover x because, well, because u covers f of x. The image, every point in the image is in some u, and then, well, okay, so this is an open cover of x. And now x compact, this implies that there exists a finite subcover. So this cover is very redundant. We only need finitely many elements to cover. So let me write it this way. So it's like f inverse of u1, f inverse of um. So then, now I want to conclude, well, so u prime being this set, u1 up to um, is a finite subcover. so this is a finite subcover of X, and this is a finite subcover of the image of X. Do I want to say anything more about that? Yeah, I mean, if you have a point f of X in the image, well, X is in F inverse of UI for some I, and so then f of X is in F inverse of UI. No, f of X is in UI. Okay, so this is why this, knowing that V prime covers X means U prime covers F of X. Okay, so that's the proof. We'll see some applications of this proposition later. Or maybe, yeah, so well, let me give you a little application now. So application, well, from this we can deduce that the circle in R squared is compact. So assuming the closed interval 0, 1 is compact, which we're going to prove eventually. Well, we have a map, the exponential map that we talked about last time. T goes to cosine t. Let's do cosine 2 pi t, sine 2 pi t. This map is continuous, and its image is exactly the circle, surjective, and so the image is compact. Right, so you could also deduce that the circle is compact using the Heine-Borel theorem, because you can argue that the circle is closed and it's a bounded subset of R2. But, well, okay, this is sort of a different argument. At the end of the day, it's the same, but using this proposition. Okay. Okay, let me give you a different, let me now mention a different proposition. So this is what we'll call the boundedness theorem and the maximum value theorem. Value theorems. So these are results that might seem familiar if you've taken analysis. So let's take X a compact space and F a continuous real valued function on X. So then, let me write that here. Then two things. So first of all, F is bounded, which is to say there exists some number M so that F of X is less than M in absolute value for all X in X. And the second, so that's the boundedness part. And then the maximum value part says that F achieves a max value, which is to say there exists some point A in X so that f of X is less than or equal to f of A for all X in X. Okay, so this part 2 strengthens part 1. Since you could just take M to be f of A, or maybe, well, part 2 also implies that any f has a minimum value. But okay, yeah, I just want to say part 2 is a refinement of part 1, because here there's just some constant, and part 2 is saying that constant, you could take it to be the value of f at some point. Yeah, I guess I should draw some picture. So like, for example, I don't know, like you could take a function which has some maybe horizontal asymptote. This is very crooked, I'm sorry. But so this function is bounded. Maybe this function is defined on 0 to infinity, bounded, but does not achieve a max value. But the proposition says that that can't happen if the domain is compact. So here, this is not compact. And well, yeah. Okay, so hopefully this makes sense. I'm not writing down an explicit formula, but right. Okay, so let's prove the proposition. I think that's the right thing to do. Now, actually, we're only going to prove part of it. So let's prove the first part, which I guess, okay, sorry, I'll leave this here and then we'll prove it on a new page. And let me just make space. Yeah, I'll erase all of this. Prove part 1. Okay, so the proof has 2 steps. We're going to start locally and observe that, so a continuous function is locally bounded, which is to say, for P and X, there exists an open set UP containing P and some number MP, so that the absolute value of f of X is less than MP for all X in UP. Okay, so for X near P, f is bounded by some constant m sub p. And the way to see this, f is continuous implies that, well, there exists some UP containing P so that x in UP implies that, well, f of x is in a small neighborhood of P. Let's just choose a neighborhood of radius 1. So f of x is between f of P plus 1 and f of P minus 1. Okay, right. So now what? Oh, right. And so then, sorry, I'm trying to decide how much to say. I mean, the picture here is I have P and f of P, and here I'm just choosing an open set of radius 1 here. And I know the preimage of that is open. Okay, V, F inverse of V, that's my UP. And right, so then I can take M sub P to be the max of, well, the absolute value of F of P minus 1 and absolute value of F of P plus 1. I mean, because these could be negative, so, well, you should take absolute value and take the max. Okay, so that's the first part. And then the second part is, well, X is covered by these U sub P's. This is an open cover. And X is compact means that, well, there exist finitely many of these that cover. So let's say there's P1 up to PS, so that X is the union, well, UP1 union up to UPS. And well, now X is bounded on each of these open sets by some constant MP. And so to show that F is bounded on all of X, we just need to take, we can just take M to be the maximum of the MPs here. So let's set M to be the max of MP1 up to MPS. So then the absolute value of F of X, for any X, X is in one of these open sets, and on this open set, if it's in UPI, then the absolute value of X is less than or equal to MPI, but that's less than or equal to M. So we have this inequality here. Okay. And that's the proof. Okay, so compactness is an extremely useful property. It allows you to pass from the infinite to the finite in this way, as we did here. And well, so as this consequence, we have continuous real valued functions are bound, which is certainly not true for any continuous function on a not necessarily compact set. I mean, yeah, so as an illustration on, you know, well, I guess you could use a function like the one I wrote down last time. This is unbounded. Looks like this, but no such function. No continuous function like this exists on a closed interval. Okay. All right, good. Right, so now I want to turn to Heine-Borel and begin to discuss some of the ingredients of the proof here. So I'll remind you, this says X in Rn is compact if and only if X is closed and bounded. So today, we'll prove the forward direction. Now, if you have a compact set, then at least it's closed and bounded. So let's do this. So let's fix X in Rn compact. And okay, so first let's show X is bounded. Well, okay, so note that X is contained in the union of balls of radius 1 about points in X. And X being compact means that, well, finitely many of these cover. So X is contained in the ball of radius 1 about P1 together with ball of radius 1 about PS for some points P1 up to PS in X, similar to before. So, well, from this, it follows that X is contained in the ball of radius 1 R about 0 for some large R. Right, I mean, we have some finite set of points. There's some balls around these points, some radius, maybe the radius is really large, or maybe not, I don't know. Okay, that's not a ball, but okay. So we know X is contained in something here, and so then I'll just take a massive ball that contains all of these, and that doesn't even contain all of them. Okay, like this. All right, hopefully you're convinced by that. But yeah, I mean, if not, you should fill in the details, try to write it down carefully. Okay, so that's the first part. Compact implies bounded. We would like to also show that X is closed. And the way we'll do this is we're going to show X complement is open. So let's fix a point Y in the complement of X. And what we want to do is find some U open so that Y is in U is contained in X complement. Okay, so here's how we can do this. For x in X, choose R sub X so that the ball of radius R sub X around X is disjoint from the ball of radius R sub X around Y. Okay, so I have some set X. It's compact. I don't really know what X looks like. There's maybe some different pieces. This is X, and I have some point Y outside of X. But maybe it's pretty close to X. I don't know. I mean, maybe it's somewhere in here. And what we're looking for is an open set around Y, small ball around Y, which is disjoint from X. And well, what we're going to do is for any point in X, so little x here, I can find a little small ball so that X and Y are those balls around a radius R, so that the ball of radius R around X and the ball of radius R around Y are disjoint. And I do this for every point. And so now X, this gives me an open cover of X. So X is contained in the union of the ball of radius Rx around X as X ranges over points in X. And now X compact means that, well, X is contained in the ball of radius Rx1 around X1 union the ball of radius XS, and now we're into triple indices. So now you know we're really doing some math here. Like this. Okay, so we can, so now let's set R to be the minimum of Rx1 up to Rxs. So then by construction, the ball of radius R around Y is disjoint from well, each of these balls, but these balls cover X, and so hence it's disjoint from X, which is exactly what we wanted. So now we have this open set contained in the complement of open set around Y contained in the complement of X. So that shows X complement is open, and so X is closed. Okay. Oh, no, I do not want to delete. I don't want that either. Okay. So I think this is a good place to stop. So next time, we'll prove the converse, that X closed for X a subset of Rn, closed and bounded implies that X is compact. So I realized there was one more thing I wanted to say at the end here, just to wrap up the discussion, which is to explain how one can give an alternate proof of the boundedness theorem using what we just proved. So here, remember this says that a continuous function on a compact set is bounded. And we want to use this theorem, we know compact sets are closed and bounded, and use the first proposition we proved, that the image of a compact set is compact here. So, okay, so let me explain how we can, right, so here's a proof of the boundedness theorem. X is compact implies f of x, which is a subset of R, is compact, which implies f of x is bounded, i.e. f of x is contained in some large ball like this around the origin, and that means exactly that the absolute value of f of x is less than or equal to m for all x and x. Okay, so now I'm really done, and yes, stop there.